course, I have to tell you how a PDE fits into the setting of catastrophe theory. So this is joint work with Maria Kreusser. She's a PhD student in the image analysis group of Carola. And yeah, let me continue with this review of catastrophe theory. Right, so I'll show you a few pictures. So you've already seen the fold bifurcation that popped up here in the Bratu problem. The model problem for this is z cubed minus parameter z. And if you look at the critical points, it's quite clear that if the parameter is positive, you have two solutions. If the parameter is negative, you have no solutions, and they merge in this way, and this is called a fold. It belongs to the A series A2. Now, this is the three-dimensional version of the picture that you've seen here of the cusp. So if I have more than one parameter, I can have more complicated bifurcations like the cusp. It belongs to the A series again. And yeah, so it looks like this sheet. If I plot the critical points over the parameter space, then it looks like this. And you'll see that fold bifurcations occur here as sub-bifurcations. So for example, here and here. And if you only draw the folds over the parameter space, then it's like looking down at the most critical points, and it will go down to this picture. Now, the statement of catastrophe theory is, even if I perturb this function a little bit, but arbitrarily, it will remain a cusp. If I have only up to two parameters in my function, then I can perturb it arbitrarily, or the only bifurcations which are stable under small perturbations are the fold and the cusp. Otherwise, there always exists a change of coordinates, and this is the splitting method that Robert has introduced here. There will always exist a change of coordinates such that you get back to this form. And this is also true if you have more than one coordinate. You can have arbitrarily many coordinates. If you only have two parameters, then there exists a change of coordinates such that you get a quadratic part plus some degenerate part, which is f, and f will be of this form, or f will be of the form of the fold, or f will also be just quadratic. So only these three possibilities are there. No bifurcation, fold, or cusp. Everything else is not persistent under perturbation. That is the statement of catastrophe theory. That's the big thing that, starting from the 60s, 70s, people started classifying which kind of bifurcations are persistent. Let me go up to 3 parameters. There we have some more possibilities pop up. So there's the next more complicated one. It again belongs to the A series. The A series bifurcations have in common that I can write down model problems with just one variable. So here each point in the sheet corresponds to a fold bifurcation. The edges correspond to cusp bifurcations, and they merge here in this very degenerate critical point in this complicated way. There are more bifurcations which are stable if I have 3 parameters, but to write them down I need more than one variable. So for example here, the hyperbolic umbilic, that's already looking quite complicated here, right? And they are gray because I need 2 variables to write down a minimal example of a hyperbolic umbilic. So you see that this line of cusps interacts with a sheet of folds in this very degenerate way. There's another one, the elliptic umbilic, 3 lines of cusps merging in this very degenerate critical points. And now the list is complete. If I have at most 3 parameters, all the bifurcations I've shown you so far are the only ones which are stable under small perturbations. So that's the great thing of catastrophe theory. And now we're not interested in these small model problems here. We're interested in the case where this function here is huge, is the discretization of the PDE. Or maybe it's the PDE itself. And yeah, how to, if this is a huge system of equations, how to actually find numerically these very degenerate points. Let me first show you how to fit PDEs into this framework. And yeah, this is not in pictures now, this is in formulas. So, simple example, which has already been started by Robert, is the semilinear Poissonequations. So the Bratu problem fits into this here, right? If I choose to be the negative of this here. So take the semilinear Poissonequation. So this is just a class U equal to minus f with Dirichlet boundary conditions. I can take the weak formulation, which looks like this. Okay, and now I see that I can write down this functional here. F bar is simply a primitive of f with respect to the variable u. So I can write down this functional here. And if I take the Frichet derivative of this functional in the direction of v, then I get exactly the weak formulation. So the semilinear Poissonequation has a variational structure because it's exactly the critical points, or the solution of the weak formulation are exactly given as the critical points of the functional. And a lot of PDEs have this variational structure. It's the thing where you would always apply a variational integrator. Okay, so there's quite a general result proved by Marston and Golubitsky, and when these two people write a paper together, then you expect some significant result, right? And this general result means that whenever I have a Hilbert space and I have a smooth functional and two simple conditions are fulfilled, then everything is governed by finite dimensional catastrophe theory. So how does it work? I start with a Hilbert space, a smooth functional, like the one I've just shown you. Two conditions are the second derivative behaves like as if it was a Hessian. The first derivative behaves like as a gradient, and then the second is true. Okay, so let's go through these two assumptions. There exists a Fredholm operator which takes the role of the second derivative. So this T here is like a Hessian matrix. And if this T here exists, then I can actually split my Hilbert space. T will automatically be symmetric, like a Hessian matrix. I can split my Hilbert space into the kernel and range. And because it's a Fredholm operator, the kernel will be finite dimensional. So this is a finite dimensional space. And I can introduce the variables x and y. Next assumption is that the first derivative of s is like a gradient. So there exists a function which I suggestively call gradient of s, right? Which plays the role of the usual gradient function here. So if E is finite dimension, then if E is finite dimensional, then all these things are quite trivial, right? So T is a Hessian matrix, and this is the usual gradient with respect to y. So if these derivatives behave nicely, then I can do the splitting lemma. The one that Robert showed you in finite dimensions can be done in infinite dimensions. So there exists a change of coordinates of these x and y's, which is actually pi by y, so I only have to change my y, but the changes of y depend on x. So there exists a change of coordinates such that s has this simple form. The simple form is, this is just a quadratic. This doesn't play a role for degenerate bifurcations, right? Quadratic functional plus something degenerate. And this means I only need, if I want to calculate how degenerate my functional is, I only need to look at this term, which is defined on a finite dimensional space, namely the kernel of T, to be precise, just on a neighborhood of 0. So that the finite dimensional space, so I have to analyze this here. I know there exists some change of coordinates, so this means I can do implicit differentiation, figure out for a given S, this R, and check the conditions, how many derivatives vanish, and so on and so forth, and then I know which singularity I have. And I've done that for you. So you don't actually have to do this, because this is all nicely written up. So what are the conditions on S, on the functional S, to have an A-series bifurcation? So first, of course, at the point 0 in this example, it needs to be a critical point. That's condition number 1. Then there is the fold condition. The fold condition works out to be this here. The kernel of the second derivative, think of the Hessian matrix. So the kernel of the Hessian matrix should be spanned by exactly one element. If there are more elements in the kernel, then I might get D-series or something like this. So if it's spanned by one element alpha, then I have at least a fold or something more degenerate. Then there is something like the cusp condition. So this is equivalent to 3 derivatives vanishing for this degenerate point here, right? So the question is, when do I have A3? And for this, I need to calculate the third derivative of S in the direction of alpha. And then it's getting a little bit more complicated, because more terms coming in if you do implicit differentiation. So then, if I want to check whether I have a swallowtail, I first need to solve the linear system, which is like Hessian matrix times what I have to solve for is this right-hand side here, and then I have to check the swallowtail condition. You can go further, so next A-series bifurcation would be the butterfly. Similar strategy, so again you have to solve for W here. So you have to solve Hessian of S times W is this term here. And then you can test an equation, and if this equation is fulfilled, this means you have at least a butterfly. If this equation is non-zero, this means you must have a swallowtail. Right. You can do it for A-series bifurcations, for the whole series, infinite dimensional series. And I think this is all that I want to show you with this slide. It all has to do with Bell polynomials. So you can work out these terms by staring at Bell polynomials. If I apply this to the semilinear Poissonequations, things become very simple. Because, well, the Laplace operator is just linear. But I mean, this stands for quite a big class of PDEs, where it becomes as simple as here for the semilinear Poissonequation. So that's the semilinear Poissonequation, right? So if I translate the fold condition back into the strong formulation, it means I need to be able to solve this system of PDEs. But this is just linear in alpha here, right? So this is quite a nice thing. The cusp condition boils down to being to checking whether this integral here is 0. And yeah, so from now on, it's just solving linear PDEs with some determined right-hand side. So here, for example, I have to solve for the B, which just appears linearly, and then I can check some condition. Here, I have to solve for the W, and this all is kind of the right-hand side, and so on and so forth for the whole A series. But how do we actually compute things?
These additional conditions, these have to be satisfied by the solution.
All together, yes.
Okay,
So
it's an additional constraint.
Yeah, so if I can solve, say, all those three things here, if I can solve all those three things here, and this algebraic condition is fulfilled, then I have a cusp or something that is more degenerate. So they all add on. So, and now I have to show you all the formulas which hold for the discrete setting. Well, I actually don't have to do this, right? Because they are the same formulas as for the continuous setting. This is a very nice thing, right? We have proven something which holds on Banach spaces, and this now applies in one-to-one if we discretize the equation using a variational integrator. Yeah, then the whole theory that holds in the continuous setting holds for the discrete version as well. So let's see how, let's do this example here. Let's do the semilinear Poisson equation. I take a two-dimensional, I take a square, and this is my functional, critical points of the functional solutions to the semilinear Poisson equation. I discretize using the variational integrator. So if there's the variational structure in the Poisson equation, and the variational structure has something to do with which bifurcations occur, then I should better preserve the variational structure under discretizations. And I do this here by just, replacing this, the integration by summation and doing some simple finite differences here for the derivatives. So this is equivalent, by the way, to doing symmetric finite, sundry finite differences in each space direction. Okay, and I take, now, as you've mentioned, to find a very high codimensional bifurcation, I would have to put all these equations below each other and then try to solve it, right? And that just doesn't work, right? Because, well, you take Newton iterations, they just, if you don't have a good initial guess for your Newton iterations. So how do you do this? The idea is the following. You first start with a simple problem, and this simple problem in this case just means solve the semilinear Poisson equation. So just get a solution. Once I have a solution, I can continue these solutions and monitor the cusp condition along the solutions, monitor the fold conditions along the solution, and check when do I hit a fold. And once I have a fold, then I add the equations for the fold to this system, and then I continue the line of folds. And now, this was already mentioned by Robert, that we actually continue solutions. And how does this, I just recall this picture. How do you continue solutions? So you assume you already have this branch of solutions, or this is the branch of solutions, and how do I get it numerically? Say I have this guess, or I have this initial, I know this solution here, so this is my parameter, and this is u. Then I make a predictor step, which is just along the tangent, and the length of my predictor step is some fixed number, call it delta s. And then I make a correction step, which goes back down to the solution. So I look for solutions of the equations such that the distance for the solution to the guess is perpendicular to this tangent space. Yeah, this is called pseudo arc length continuation because it's like stepping along the arc length, but actually it's not parameterized by arc length, but actually by these predictor steps, by some linearization of the arc length. So this is a standard method, and it works very well. So here you see how it's working. I start just with a simple zero solution, and I continue the solution, and during this, I just monitor whether the parameter suddenly starts decreasing. So first the parameter increases, and then suddenly the parameter starts decreasing, and then I know there must be a fault. Okay, and now I add to this equation, which just means solutions to the Poisson equation, or to the semilinear Poisson equation, I add the fault condition. The fault condition was essentially that the Hessian matrix is singular. So this means there exists some alpha here, such that this vector alpha here is mapped by the Hessian to 0, and alpha is not a 0 vector. So this is the new condition for a fault. If I had tried directly to solve these equations for a fault, my Newton iterations wouldn't have converged without a good initial guess. But now I have a very good initial guess from the last time, right? Because I have a starting fault. Okay, so I apply my continuation method to this equation here, starting here, and this will draw me this blue line. The blue line, you have to think of this blue line as being actually smooth in the space, parameter times phase space. It's actually smooth. But it looks non-smooth here if I just plot the parameter values. But so there's no problem in following this line. And during this following, I always monitor whether the cusp condition is fulfilled. Once it's fulfilled, I make a little dot and know, okay, round there is a cusp. So I mean, I see when this here changes sign. And I don't need to worry about finding the cusp up to high accuracy because I just need a good initial guess for my next step. And my next step is to add the cusp condition to this here and continue a line of cusps. So this here was a line of faults, and now in the next picture, this is a line of cusps. So this is the new augmented system that I need to continue, and this will draw me this blue line here, and during this, I monitor the swallowtail condition. So I monitor when does this here change sign. And now there's a little bit of a tricky thing going on here. I'm not sure whether you've noticed, but I sometimes told you like, yeah, solve this equation, but there was actually a singular matrix standing, right? So there was you often have to solve something like Hessian of S at 0 times a vector is something on the right-hand side, and the matrix that was on the left-hand side was actually singular. And this happens here. Here I have to solve the Hessian of S times V. I need to solve for V is equal to this here. And theory guarantees me that this solution exists, but, well, numerics is a little bit different. So I put this into this minimization problem here. I just add the element of the kernel, and then I minimize this using standard numerical tricks. The theory doesn't see this problem because it says just, well, restrict to the range of this symmetric operator, and there it's an isomorphism. Right? This is why we didn't see the problem when I went through the theory. But you have to think of some numerical tricks if you actually want to compute this. Anyway, here we find a swallowtail, and this was our aim, finding a high codimensional bifurcations in a PDE, or showing proof of concept how to find these these high codimensional bifurcations in a PDE, because they actually make you understand your solution space. If you know which bifurcations occur, you know roughly how your solution space looks like and how your solution branches interact. How do we actually know that's a swallowtail? It could also be a D-series bifurcation, you could say, right? I mean, first thing I should check is if I perturb my equation, does it remain? Is it persistent under perturbations? Check that, so I know it must be one of the catastrophes from catastrophe theory, because it's nothing related to symmetry. So it must be a swallowtail or one of the amphilids. And then we can look at the swallowtail condition, and it goes nicely through 0. And the other two candidates, which are the D-series bifurcations, they diverge and don't go through 0 if I monitor the swallowtail condition. Of course, I could also check whether the Hessian matrix only has a one-dimensional kernel and not a two-dimensional kernel. That also excludes the D-series bifurcation. But, again, numerically checking this could be tricky. And also what you should... Another way of verifying this is, well, we know how the swallowtail is supposed to look like. So just start a fold continuation near the swallowtail point, fix one parameter, and then it looks like this. So the line of folds will find the other line of cusps, bounce back, and essentially do this move here. And this is exactly what we expect from this figure. Then you remesh and see that that this is not an artifact of the discretized system, and see that the point of the swallowtail actually converges. And yes, then you know that in your PDE there's a swallowtail for these values of parameters. All right. So what have we done? We actually have derived recognition equation, and this is kind of the new thing, that we actually make use of a gradient structure. We use the infinite dimensional splitting lemma. And I haven't seen this in the literature, that someone has actually calculated and used this for numerical computations. And it's quite important because the PDE has a variational structure, so you should take account of that. Usually, if you don't have the variational structure, and the literature is full of this, then you use Lyapunov-Schmidt reduction as rather than the infinite dimensional splitting lemma, and you can derive these kind of recognition equations. So we've done this in the variational case, and yeah, nice thing is we can treat all A-series bifurcations in a unified way, and the continuous problem and the discretized problem, they share exactly the same theory if I use a variational integrator. We haven't done a numerical example for the D-series bifurcation yet, and so this is left for future research. And it would also be good to know whether it's possible to get some a priori error estimates of the location of the bifurcation in the discretized system and the position of the bifurcation in the real system, in the actual PDE. But it's not that easy, because you need to, well, you're looking at singular points. That's the whole tricky thing. Yeah, so thank you for listening.
Any questions? I do have a question. I may have missed this. But this unified treatment that holds for small.
So you mean what I mean here with unified treatment of the continuous and the discrete setting?
Yeah, but I assume that there's some sort of discretization parameter.
Yes.
And that this only holds for small values of the discretization parameter.
So what I mean here is that the formulas that I need to check, or the equations which need to hold to know that a certain system has a certain bifurcation, they are the same for the continuous setting and for the discrete setting.
And we also know that the bifurcation equations of the discretization is the same as discretizing the continuous bifurcation that commutes.
There's some that commutes.
What we don't know is the last line is are the solutions close together? Are the solutions of the discrete system close to the solutions of the continuous one? But I guess I still don't know the answer to my question. I assume there's some sort of parameter which in the if you take the limit, continuum limit, this parameter goes to 0, right? Now surely this doesn't hold for arbitrary values of that parameter.
You mean if you make the parameter very large, that the perturbation becomes so large that something like a cusp structure is destroyed? We don't have error estimates for these things, right?
Well, so that's what I'm saying. So that maybe there's not an online. I mean, could that's the question. That's exactly it. Yeah, no.
Yeah, I mean this clearly depends on the condition of the system. If your cusp is so small, is smaller than your age, right? Than your discretization age, then of course the discretized system does not have the cusp. So this really only holds in the limit.
Yeah, but sorry, but there we're talking about the parameter lambda, right? That's not the same as a discretization parameter.
Yes, but they can trade in the following sense. If I take this problem here, right, the Bratu problem with 2 parameters, the continuous Bratu problem with 2 parameters, it has a cusp. Now the discretization. Now I discretize this problem. This will introduce another parameter h. But this parameter is fixed. I fix the parameter and then I start calculating. And this is fixed and small. This is like throwing in a very, very small perturbation term here. And some perturbation term. Let's call this, I haven't used epsilon yet. So this is like throwing in some very small perturbation term. And this perturbation term is thrown in the way I'm computing. The perturbation term is thrown in a way that the gradient structure is not destroyed. This means that I just perturb this problem here slightly, and I know that the cusp is stable under small perturbations. I have no error estimates how small these perturbations are supposed to be. But sufficiently small perturbations will leave the cusp invariant. So it will move to another parameter value. So it will not be at the same position anymore, and it will look a little bit askew, but it will still be a cusp.
But you're saying that when you've actually done examples numerically, this turns out often to be a small perturbation.
Yeah, I mean, of course, you can think of some arbitrarily large, arbitrarily bad discretization where the step hops over your cusp and then everything is destroyed, right? Take this example here of the swallowtail. We just had a grid which was 15 times 15. So that was 225 grid points. And the whole boundary was taken up by the Dirichlet problem. and there it worked nice and well. Of course, then you have to verify. It would be so. As far as our theory goes, it would be bad just to stop at this one simulation, right? So what I've also done is once you've found using this thing here, once you've found the swallowtail in the discretized version, you just interpolate all the data that you have from this point and use it as a good initial guess to solve the same system here for a discretization with more grid points, and then see whether Newton converges or not. And if it does, yeah, then you know there's actually a swallowtail bifurcation. But it would be nice to have some a priori error estimates, right?
The guess would be that if you took a variational finite element method of a certain order, then you should get to see the same order of convergence for the augmented system, even though the linear operators are now singular. That would be the hope. Oh, it's a...
Okay, on your poster you have pictures of these embeddings. Here you say that you still need to do more on it. So what is it exactly that you want to look at?
Right, so on my poster, I showed you what actually happens in the ODE case, in the finite dimension.
Oh, that's for the ODE
case. And also one thing in my poster was what happens if you destroy the gradient structure, if you use a non-symplectic integrator. You can see this in this project as well, which refers to using a non-variational integrator. And then you wouldn't be able to find an abylic bifurcation. But we haven't come to the D-series yet in this thing. But for D-series bifurcations, it's crucial for exactly that reason that you use a variational integrator. If you destroy the variational structure, the D-series bifurcation will not be persistent anymore, and then your little small discretization error will be exactly this perturbation that destroys your bifurcation. If you use a variational integrator, the D-series bifurcation is stable, and then your little small discretization error will not destroy the bifurcation. It will just move the bifurcation to another point.
Okay, let's thank Christian again.